Hey everyone, tonight we're stepping into the quietest, most desolate laboratory you can imagine to witness an experiment that, by all logic, should never have worked. An experiment that eventually led to, well, picture this. We're standing on the surface of Earth exactly 66 million years ago, but this isn't the lush, vibrant planet you know. Before you lies a scene of absolute devastation. A 10-kilometer wide asteroid has just slammed into the Gulf of Mexico, and the world is burning. The sky is choked with soot and vaporized rock, plunging the planet into a twilight that will last for years. The air is thick with sulfur, and acid rain pours from blackened clouds. The great dinosaurs, rulers of Earth for 150 million years, are dying. Their reign ends not with a slow fade, but with a sudden, violent apocalypse. From this planet-sterilizing catastrophe, let's narrow our focus. Hidden in a shallow burrow beneath the scorched ground, a creature no bigger than a mouse trembles. It's a mammal, a member of a group that has spent its whole existence living in the shadows, darting through the night to avoid becoming some reptile's next meal. To this tiny, furry survivor, the end of the world is just another reason to stay hidden. But within its fragile body lies a secret. It carries the improbable, almost laughable potential for everything that is to come. Over millions of years, its descendants will emerge from their burrows into a strangely empty world. They'll climb trees, grow larger, and evolve brains of astonishing complexity. They'll witness ice ages, drifting continents, and the rise and fall of countless species, all while conducting a quiet evolutionary experiment centered on one continent in particular. So, how did this happen? Out of all the continents on Earth, why did this one specific lineage, on this one specific landmass, Africa, eventually lead to a creature capable of looking up at the stars and wondering about its own existence? What made the African experiment so unique? And what secrets do its rocks and fossils hold about the deepest origins of our identity? Thanks to a century of fossil hunting and revolutionary genetic technology, tonight we'll travel back through the eons to piece together the clues and uncover the answers. Frankly, if you were dropped into this post-apocalyptic world without a time machine, you'd last about as long as a snowflake in a furnace, and your biggest problem would probably be avoiding an overly ambitious shrew. Before we dive in, take a second to like this video and subscribe, but only if you genuinely enjoy what I do here. That small click sends a big signal to the algorithm that long-form, serious educational storytelling still matters, and to me, it's an incredibly meaningful show of support. I always love seeing where you're tuning in from. Drop a comment with your country and what time it is for you right now. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. Your first sensation in this new world, the Paleocene epoch, is silence. The thunderous footsteps and bone-shaking roars of dinosaurs are gone, replaced by the whisper of wind through skeletal forests. The planet is slowly recovering from a fever. The impact winter, when dust blocked out the sun, is giving way to a greenhouse climate. But the ecosystem is only a ghost of what it was. The fossil record shows what paleontologists call a fern spike, a period when the world was carpeted with ferns, the first rugged colonizers of a wounded planet. It's a world waiting for new rulers. A planet with a help-wanted sign hanging over it. There's a power vacuum on a scale the world has never seen before, and our distant ancestors are about to apply for the job. This moment in time marks the great mammalian radiation, a cornerstone of evolutionary biology. Imagine a handful of people suddenly waking up in a massive empty city, grocery stores fully stocked, apartments vacant, cars with keys in the ignition. With no competition and endless resources, they could spread out, specialize, and build new communities almost overnight. That's exactly what happened to mammals. For 150 million years, they'd been confined to a few small niches, mostly tiny, nocturnal insect eaters. But with the dinosaurs gone, every niche was suddenly open. Within just a few million years, mammals exploded into astonishing diversity. Some became large herbivores, others fearsome predators. Some returned to the water, others took to the air. It was a chaotic, creative explosion of life, and among all the evolutionary experiments underway, one was particularly important to us. It was a small creature called Purgatorius, discovered in the Hell Creek Formation of Montana, the very same rocks that hold the last fossils of Tyrannosaurus rex. Named after a nearby hill called Purgatory Hill, Purgatorius was tiny, lighter than a golf ball, and looked much like a modern tree shrew. It scurried through the recovering forests of North America, feasting on insects making their own comeback. At first glance, it was unremarkable, but when scientists studied its fossilized ankle bones, the talus and calcaneus, they noticed something extraordinary. These bones allowed a great deal of rotation and flexibility, a key adaptation for gripping and pivoting on uneven surfaces, perfect for climbing. It was the humble beginning of an arboreal lifestyle, the first step into the three-dimensional world of the forest canopy, the cradle of primate evolution. This, of course, sparked a classic scientific debate. Was Purgatorius a direct ancestor of ours, a true proto-primate sitting at the base of our family tree, or just a close cousin experimenting with similar traits? Was it our many times great-grandfather, or more like a great-uncle with a similar job? The fossil record is sparse, the lines blurry, but one thing is clear. Just moments after the dinosaurs' extinction, the evolutionary experiment that would lead to primates, and eventually to us, had already begun. Not in Africa, but in the quiet, fern-covered forests of ancient North America. As you watch little Purgatorius scamper up a fallen log, you're not just looking at a single animal, you're witnessing the start of an idea. The idea of leaving the forest floor behind. But evolution is never a straight path. It's more like a wildly branching bush, with countless stems reaching for the light, most destined to wither and die. For the next 10 million years, the branch that truly flourished wasn't ours. It belonged to a far more successful group of early primate cousins, known as the Plesiadapiforms. If Purgatorius was the quiet opening act, these creatures were the headliners of the Paleocene. Picture a world where the continents are still drifting into place, North America, Europe, and Asia, often connected by land bridges, forming a massive forested supercontinent called Laurasia. Across this vast landscape, the Plesiadapiforms thrived, a worldwide experiment in what a primate-like mammal could be. With dozens of species adapting to every niche, they became some of the most common mammals of their time. Their tiny fossilized jaws and teeth have been found everywhere, from Wyoming to France, silent witnesses to the dawn of our story. They were the original pioneers of the arboreal world, but if you were to see one, you wouldn't immediately think primate. Your first thought might be squirrel, lemur, or perhaps some strange combination of the two. They had long, bushy tails and agile bodies built for a life of scampering and leaping through trees, but their teeth told a more complicated story. While their back teeth were primate-like molars, perfect for grinding fruits and insects, their front teeth were large and gnawing, almost like those of rodents. And most importantly, when you look at their skulls, you notice their eyes were positioned on the sides of their heads. They couldn't merge their fields of vision to create the stereoscopic 3D view of the world that you and I take for granted. They saw in flat, two-dimensional panels, a trait that gave them a wide field of view to spot predators, but lacked the precise depth needed for daring leaps through the tangled canopy. They were, in a sense, a rough draft, an early attempt at building a primate. Within this diverse group, however, evolution produced some truly fascinating experiments. Take, for instance, a plesiadapiform called Carpalestis, which lived in North America around 56 million years ago. This small creature gives us a quirky, fantastic glimpse into evolution's trial and error process. While the rest of its body was fairly ordinary, its big toe was a masterpiece of convergent evolution. It was opposable, much like your thumb, allowing it to grasp branches with incredible strength. And at the tip of that toe, it didn't have a sharp, curved claw for digging or fighting. Instead, it had a flat nail. That single detail is a hallmark primate feature, showing up millions of years early on a creature that wasn't a true primate at all. Carpalestis had independently evolved the perfect tool for gripping the slender ends of flowering branches to reach fruit and nectar. A full primate-style pedicure, millions of years ahead of schedule. The evidence for the lifestyle of these animals is written directly into their teeth. By examining the microscopic scratches and pits on the enamel of fossilized plesiadapiform molars, a field known as microwear analysis, scientists can deduce their diet. The patterns reveal meals rich in soft fruits and crunchy insects. That diet was the secret to their success, but also the seed of their downfall. By specializing in this menu, they entered direct competition with two other rapidly evolving groups, the true rodents, whose ever-growing incisors made them far better gnawers, and another, newer lineage that was developing a secret weapon for finding fruit in the dappled forest light, our own ancestors, the first true primates. This brings us to the great debate surrounding these fascinating creatures. For many years, they were called archaic primates and placed at the very base of our family tree. But now, the consensus has shifted. While they are certainly close relatives, they are not our direct ancestors. They represent a side branch, a lineage that explored a similar ecological niche, but ultimately reached an evolutionary dead end. They lacked the full primate toolkit. They didn't have forward-facing eyes for depth perception, their wrists and ankles were less flexible, and their brains were relatively small. They were a grand, successful experiment that lasted for over 10 million years. But as the world changed and new, more specialized tree dwellers evolved, the plesiadapiforms were slowly outcompeted. Their story is a powerful reminder that our own evolution was never guaranteed. It was just one of several competing ideas, and for a long time, it wasn't even the most successful one. As the world drifted out of the Paleocene, the plesiadapiforms, for all their success, began to fade from the fossil record. They became relics of a bygone era, as the planet itself transformed in ways that favored a new kind of animal. You are now entering the Eocene epoch, beginning around 56 million years ago, and the first thing you notice is the heat. The Earth has become a global hothouse, a sweltering, humid greenhouse of a planet. It was one of the warmest periods in the last 66 million years, a time with little to no ice at the poles. Fossils of palm trees in Alaska and crocodiles in the Arctic Circle paint a picture of a world almost alien to our own. This relentless warmth and humidity fueled vast, dense tropical forests that spread across the continents, a three-dimensional superhighway of branches and vines. This was the perfect laboratory for evolution's next great leap, a world waiting for the rise of the true primates. And right on cue, they arrive. Emerging into these boundless forests are the animals paleontologists call the euprimates, meaning true primates. They appear almost simultaneously in the fossil record of North America, Europe, and Asia, and are divided into two main groups. First, the adipids, generally larger, slow-moving climbers, somewhat like modern lemurs. They were likely diurnal, active during the day, and their teeth suggest a diet of fruit and leaves. Then, the hominids, smaller, more agile creatures with large eye sockets that hint at nocturnal habits, much like modern tarsiers. They were expert leapers, hunting insects under the cover of darkness. Despite their differences, both groups shared the full evolutionary toolkit that defines our order, the very traits that separated them from the Plesiadapiforms and set our lineage on its path. Let's break down this toolkit. These aren't random traits, but a suite of interconnected solutions to one complex problem: how to live in the trees. First, their grasping hands and feet. Unlike the clawed digits of their squirrel-like ancestors, primates had long, opposable fingers and toes tipped with flat nails. This gave them a powerful grip for clinging to branches of all sizes, and manual dexterity to hold and examine objects, like a piece of fruit, before eating. Second, their forward-facing eyes. By bringing the eyes to the front of the skull, their visual fields overlapped, creating stereoscopic vision or true 3D sight. For an animal that leaps from branch to branch, judging distance and depth with pinpoint accuracy isn't optional. It's a matter of survival. One misstep, and you become a fossil on the forest floor. Finally, to process all this rich visual information, their brains had to evolve. They were significantly larger relative to body size, with expanded regions devoted to sight and reduced areas for smell. They began to navigate their world less by snout and more by sight. For decades, the simple explanation for this toolkit was the arboreal hypothesis that these traits were simply adaptations for tree life. It makes intuitive sense, but it has one glaring flaw: squirrels. Squirrels are superb tree climbers, and they manage just fine without forward-facing eyes or grasping hands tipped with nails. Clearly, just living in trees wasn't enough. This led to the visual predation hypothesis, a more compelling idea suggesting that early primates were stealthy hunters of insects and small prey in the lower forest canopy. In this view, grasping hands were for snatching fast-moving prey, and 3D vision was for targeting them with deadly precision in a cluttered environment. A third idea, the angiosperm radiation hypothesis, links our evolution to the explosive spread of flowering plants. As forests filled with fruit and nectar-bearing plants, a new niche opened up. Primates that could use color vision to spot ripe fruit among green leaves and had fine motor control to pluck it from thin branches held a massive advantage. In truth, there was likely no single cause. Instead, it was a perfect storm of evolutionary pressures. The trees provided the complex three-dimensional arena. The abundance of insects offered a high-protein prize for those who could hunt effectively, and the rise of flowering plants presented a high-energy, sugary reward for those who could see and grasp it. Each pressure pushed in the same direction, favoring better hands, sharper eyes, and bigger brains. Over millions of years, in the warm, sprawling forests of the northern continents, this combination forged the fundamental blueprint of a primate, a blueprint that would one day journey south to a new continent and evolve beyond imagination. For millions of years, the world of the Eocene belonged to the Adipids and Hominids, the undisputed masters of the canopy, a thriving dynasty of true primates that filled the great northern forests. But evolution, as always, never stands still. As the lemur-like and tarsier-like creatures continued their reign, a new and fateful chapter in our story was about to begin, not in the well-explored fossil beds of Wyoming or Paris, but far to the east. Now, turn your gaze away from the northern continents and toward the sweltering tropical jungles of ancient Asia. It was here, in this vast and vibrant greenhouse world, that a new kind of primate quietly emerged from the shadows of evolution. This new group, the anthropoids, marked one of the most important upgrades in our entire history. This is the lineage that would include every monkey, every ape and every human who has ever lived. The evidence for this crucial turning point in our story is tiny, fragile, and utterly fascinating. It comes from a creature called Eosimias, a name that beautifully translates to dawn monkey. Discovered in China and dating back an astonishing 45 million years, the fossils of Eosimias are so small they could easily fit in the palm of your hand. This was no great swinging ape, but a tiny creature, perhaps the size of your thumb, that spent its life weaving through a world of giant leaves and towering trees. For a long time, the origins of the anthropoid lineage were a complete mystery, a frustrating blank spot in the fossil record. But Eosimias and its relatives helped fill that gap, and in doing so, they pointed to a completely unexpected place of origin. So how can scientists be sure that this tiny animal was one of our earliest anthropoid ancestors, and not just another primitive primate? As is so often the case in paleontology, the secret lies in the small details, specifically in the shape of its ankle. The fossilized heel bone, or calcaneus, of Eosimias is fundamentally different from that of the more primitive, lemur-like adapids. Theirs were typically long and slender, built for powerful leaps. Eosimias, by contrast, had a short, sturdy heel bone. This small detail is a crucial piece of biomechanical evidence. It tells us that this animal wasn't a specialized leper. Instead, it moved through the trees much like a modern marmoset or tamarin, scurrying and walking along branches, using its grasping feet for balance. This subtle shift in movement marked a major evolutionary turning point, a move away from the tarsier-like leaping of the hominids and toward the more generalized, four-limbed motion that would one day define monkeys and apes. And Eosimias wasn't an isolated case, not a single oddity in the fossil record. Evidence for an Asian origin of our lineage has grown into a strong scientific consensus. In the ancient forests of Myanmar, paleontologists have unearthed other early anthropoids like Amphipithecus and Pondongia. In Pakistan's Bugti Hills, still more fossils have been found. Together, they paint a consistent picture. By 40 to 45 million years ago, the forests of Asia were home to a thriving, diverse community of the world's first higher primates, the pioneers of a new way of life. While their cousins in North America and Europe clung to the old ways, this Asian group was evolving key features, subtle changes in their teeth, skulls, and ankles that would define the future of the primate order. Imagine this world for a moment. You stand in a dense, dripping Eocene rainforest. What will one day be southern China? The air is thick with the scent of damp earth and blooming flowers. The canopy above is so dense that the forest floor lies in a permanent twilight, pierced only by shafts of golden sunlight. The air hums with insects, punctuated by the cries of strange birds. And high above, moving carefully along a thick, moss-covered vine, is your ancestor, a tiny, furry creature with large, curious eyes, methodically searching for insects, ripe figs, and flower nectar. It was a world of immense opportunity, but also immense danger, with primitive carnivores and giant snakes lurking in the shadows. This was the world that created the first anthropoids, an Asian cradle of our kind. But the greatest chapter of their story, and ours, would not unfold here. For reasons still unknown, this promising new lineage would have to leave its ancestral home and embark on an impossible journey to a new continent, an island landmass to the southwest. Africa. Now, you stand at the heart of one of evolution's greatest mysteries. We know two critical facts. First, the dawn monkeys, the earliest anthropoids that form the trunk of our own family tree, evolved in Asia. Second, nearly all later chapters of human evolution, bipedalism, tool use, and rising intelligence, happened in Africa. This creates a fascinating paradox. How did our tiny, tree-dwelling ancestors get from point A to point B? It wasn't a simple stroll through the woods. The journey from the rainforests of Asia to the shores of ancient Africa meant crossing one of the most formidable barriers in the history of life on Earth. To grasp the scale of this challenge, you have to erase the modern world map from your mind and picture Earth as it was 40 million years ago. Africa wasn't connected to the Middle East as it is today. It was a vast, isolated island continent, much like modern Australia, completely surrounded by ocean. To its north lay the immense, warm and deep Tethys Seaway. This wasn't just a channel. It was a true ocean, stretching from the Atlantic in the west to the Indian Ocean in the east, cutting off the southern continents from Eurasia. For a small land animal, this was a barrier as absolute as outer space. To understand how our ancestors overcame it, we need to zoom out, far beyond the scale of human time, to the slow, powerful movements of Earth itself. Beneath our feet, the planet's mantle churns like a cosmic lava lamp. Heat from the core warms the rock below, causing it to rise in slow, buoyant plumes. As it cools, it sinks again, creating convection currents that drive the drifting of continents. In our story, three great tectonic plates take center stage: the massive African plate, the smaller Arabian plate, and the enormous Eurasian plate to the north. For tens of millions of years, Africa and Arabia were slowly drifting northward, driven by those deep mantle currents, on a collision course with Eurasia. Between them lay the shrinking Tethys Seaway, caught in a planetary vice. We know this ancient ocean once existed because its fossils are still with us, locked in the rocks of the Italian Alps, the Zagros Mountains of Iran, and even the towering Himalayas. High in those peaks, you can find the remains of whales, sea turtles, and other marine life, proof that these mountains were once seafloor, pushed skyward by the immense forces of plate tectonics. This is how we know with certainty that a vast ocean once separated our ancestors from their future home. Now return to our tiny 40-million-year-old relative, clinging to a branch in an Asian jungle. Its entire world may have spanned just a few square miles. It couldn't swim across a river, let alone an ocean hundreds of kilometers wide. It couldn't build a raft or navigate by the stars. To this little creature, the Tethys Ocean was the edge of the universe. A land migration seemed utterly impossible. And yet, somehow, they made it. The African fossil record is clear. The dawn monkeys arrive, as if by magic, on this isolated continent. This impossible journey tells us one thing: the planet itself must have changed, creating a brief, miraculous pathway that allowed our ancestors to cross the void. Their journey was not a single heroic leap, but the patient work of geology, the earth itself shaping the route. As the African and Arabian plates continued pushing north, the Tethys Seaway narrowed and began to vanish. Deep beneath modern Ethiopia, a massive plume of superheated rock rose from the mantle, a colossal blowtorch lifting the land to form the Ethiopian highlands. This tectonic uplift, combined with the northward drift of the continents, warped the ocean basin. Volcanoes erupted through thinning crust, building new land where only water had been. Over time, a scattered chain of volcanic islands, an archipelago, emerged across the shrinking sea. These islands became stepping stones, the bridge between Asia and Africa. The great migration that followed wasn't a conscious trek. Our ancestors didn't set out to explore. It was slow, accidental, and incredibly rare. What scientists call sweepstakes dispersal. Picture the scene. A violent monsoon lashes the coast of ancient Arabia. A flood tears loose a chunk of riverbank, a tangled raft of trees and soil. Clinging to it, swept out to sea, is a small, terrified family of dawn monkeys. Most of these voyages ended in tragedy. The rafts were breaking apart, and their passengers were lost to the sea. But every once in a while, against all odds, one of these rafts would survive, carried by the currents until it finally reached the shores of a new volcanic island. There, a new colony would begin. Generations later, the same unlikely event might happen again, sweeping their descendants from that island to the next, and then to another, leaping from island to island across a constantly changing ocean. Eventually, they would reach the northeastern coast of Africa. This process of island hopping took millions of years, but by around 20 million years ago, it was complete. The final ocean gap had closed. When the Arabian Plate collided with Asia, it sealed off the eastern Tethys Sea forever, creating a permanent bridge of dry land connecting the two continents. Paleontologists call this formation the Gomph Land Bridge, named after Gomphotherium, a four-tusked, elephant-like animal that was among the first to use this new highway. The opening of this land bridge triggered one of the most important faunal exchanges in Earth's history, a two-way migration. The ancestors of giraffes, cats, and antelopes poured out of Eurasia into Africa for the first time. In the opposite direction, the elephant-like Gomphotheres, and most crucially, the African primates, began to migrate out of Africa into Asia and Europe. Africa's splendid isolation had come to an end, but our ancestors were the true pioneers. They had already made the far more perilous, chance-driven voyage across the volcanic stepping stones long before the easy land route existed. They had arrived in their new island home, a vast continental laboratory that would shield them from a coming global crisis and set the stage for the next, even more dramatic chapter in our story. Having survived that lottery-like journey from Asia, our anthropoid ancestors had made it. They now lived on the great, isolated island continent of Africa. They were pioneers, early colonists who had arrived millions of years before the Gomphotherium land bridge would open the floodgates to mass migrations from Eurasia. This long era of isolation was perhaps the greatest gift the planet ever gave to our lineage. Africa, during the Oligocene epoch, around 30 million years ago, was a continent-sized evolutionary laboratory, a primate refuge where our ancestors could evolve and diversify, free from the intense competition they had once faced in Asia's crowded forests. This is a textbook example of adaptive radiation. When a group of organisms enters a new environment full of open ecological niches, they rapidly evolve into many different forms, each adapted to a unique way of life. That's exactly what happened to the first African anthropoids. With a whole continent's worth of fruits, leaves, and insects to exploit, they flourished. New species emerged, some larger, some smaller, some adapted to eating tough leaves, others to soft fruits. It was during this creative burst that the next great split in our family tree took place, a division that would send one branch on an even more improbable journey than the one before. The anthropoids split into two great lineages, one giving rise to the Old World monkeys and apes, and the other to the New World monkeys. But there was a problem. The ancestors of all monkeys in Central and South America somehow had to travel from Africa to the New World. 40 million years ago, South America was still an island continent, separated from Africa by the widening Atlantic Ocean. This sets up a journey so extraordinary that it makes the island hopping from Asia seem trivial by comparison. The leading and frankly mind-boggling hypothesis for how they achieved it is known as the Great Rafting Adventure. Picture this: a colossal storm, a hurricane of unimaginable power slamming into the coast of West Africa. A great river, swollen with floodwaters, rips loose a massive piece of its delta. A floating island of trees, tangled roots and soil, perhaps several acres wide. On this accidental arc, a small group of primitive monkeys becomes stranded. Then, they are swept out into the Atlantic. At this time, the ocean was much narrower than it is today, perhaps only about 1,000 kilometers across. Even more importantly, the prevailing winds and ocean currents flowed from east to west, acting like a natural conveyor belt. Still, the journey would have been a terrifying ordeal, lasting weeks. The monkeys would have survived on whatever fruits and insects clung to the raft, licking rainwater from leaves to stay alive. It sounds impossible, a tale fit for science fiction, and yet the evidence suggests it truly happened. By sheer luck, one or more of these floating islands must have completed the transatlantic crossing, washing ashore on the coast of what is now Brazil or Colombia. There, in a land full of life but completely devoid of primates, they had struck the ecological jackpot. Scientists still debate the exact mechanism, but fossils and genetics both point to an African origin for the New World monkeys as the only explanation that fits all the facts. The earliest monkey fossils in South America appear suddenly in the record around 26 million years ago, and they look strikingly similar to their African relatives of that era. Even more tellingly, their DNA leaves no doubt. New World monkeys are far more closely related to the Old World monkeys of Africa than to any other primate group on Earth. As wild as it sounds, the rafting hypothesis fits perfectly. While their adventurous cousins sailed west to populate a new continent, our story turns back to the ones who stayed behind in Africa. The stage was now clear. Those who remained, the ancestors of baboons, macaques, gibbons, orangutans, gorillas, chimpanzees, and ultimately us, were now the sole inheritors of the Old World. They had Africa all to themselves, a vast natural laboratory where evolution would work its greatest experiments. And in this crucible of change, a new kind of primate was about to emerge, larger, smarter, and more capable than any before it. The first apes. Your journey now moves forward in time into a new epoch. The Oligocene gives way to the Miocene, beginning around 23 million years ago. Africa is changing once again. As the continent drifts northward, the climate becomes more seasonal. The once unbroken forests begin to fragment, giving way to a patchwork of jungle, open woodland, and river forests. It's in this more varied and demanding environment that the next great innovation in primate evolution takes shape. The age of monkeys is ending, the age of apes is beginning. Before meeting these new creatures, it's important to understand what separates an ape from a monkey. It's more than just a name, it's a complete evolutionary redesign. The most visible difference is the absence of a tail. Where monkeys use long, sometimes prehensile tails for balance, apes have only a small tailbone, a remnant of their distant past. Apes are also much larger, more upright, and equipped with a revolutionary shoulder joint that allows a full 360-degree range of motion, something monkeys could never achieve. But the biggest upgrade happened inside the skull. Apes have larger brains relative to their body size, bringing with it complex social lives, tool use, and problem-solving abilities. The leap from monkey to ape wasn't a small tweak. It was a full-scale evolutionary reboot, a bet on intelligence and adaptability instead of sheer numbers. And in the early Miocene forests of East Africa, we meet the perfect fossil to showcase that transition. Proconsul. Living around 20 million years ago in what is now Kenya and Uganda, Proconsul was among the earliest and best-known fossil apes. It wasn't a single species, but a diverse genus, with members ranging from the size of a small baboon to that of a female gorilla. And when you study its skeleton, you see a creature perfectly balanced between two worlds, a living mosaic of the old and the new. In many ways, Proconsul still moved like a monkey. Its spine was long and flexible, and its arms and legs were nearly the same length. That tells us it didn't swing below branches like modern gibbons. Instead, it walked along the tops of branches, on all fours. A mode of movement called arboreal quadrupedalism, just like its monkey ancestors. but the telltale signs of its ape identity are unmistakable. It had no tail. Its skull was more rounded, housing a relatively larger brain, and its teeth, with their thin enamel, were clearly adapted for eating soft, ripe fruits, a favorite food of many modern apes. The most convincing scientific evidence for its transitional nature comes from its joints. When paleontologists examined the elbow of proconsul, they found a structure built for stability, much like that of a monkey, perfect for bearing weight while walking along a branch. But when they looked at its shoulder, they saw the beginnings of that classic ape flexibility, a wider range of rotation that, while not yet suited for full-fledged swinging, was clearly a step in that direction. Its hands and wrists also show greater freedom of movement, more rotation and bending. It was an animal whose body plan was still rooted in the monkey way of life, yet it was already experimenting with the anatomical tools that would one day let its descendants hang, climb, and swing with incredible grace. This mix of features makes its exact place on our family tree a topic of friendly debate. Was proconsul our direct great-great-grandfather, or was it more like a great-uncle, part of a closely related branch that shows us what our true ancestor might have looked like? For our story, it doesn't really matter. We can think of proconsul as a perfect model ancestor, a living snapshot of evolution in motion, a creature that shows exactly what the missing link between monkeys and apes would look like, and most importantly, its fossils are found in abundance in Africa. The first chapter of the ape story, the chapter that sets the stage for our own arrival, was written here, in the warm, seasonal woodlands of Miocene Africa. The evolution of the first apes, like proconsul, was a spectacular success. But Africa was not big enough to contain it. For a time, the story of the apes was about to go global. Thanks to the permanent land bridge now connecting Africa to Eurasia, these new, large-brained primates were no longer confined. And as they stood on the threshold of a new world, the world itself rolled out the welcome mat in the form of a dramatic planet-wide heatwave. You are now in the middle of the Miocene climatic optimum, a period of intense global warming that peaked around 15 million years ago. Temperatures soared, and warm subtropical forests, the perfect habitat for apes, spread across the globe. This created a lush, green superhighway stretching from the heart of Africa across the Middle East, deep into Europe and Asia. For the various ape lineages, this was a golden age, a window of opportunity to expand and conquer new worlds. And that's exactly what they did. What followed was the great ape diaspora, a mass migration out of Africa that saw these remarkable creatures spread across 3 continents. The fossil record from this time is rich and thrilling, revealing a world teeming with an incredible diversity of apes. In the forests of Europe, from Spain to Hungary, you would have found the genus Australopithecus. With its long arms and flexible joints, it was a skilled brachiator, a master of swinging and climbing through the canopy with a grace its ancestor proconsul could never match. Further south, in what is now Spain, paleontologists discovered Australopithecus, the so-called swamp ape, showing a blend of primitive and advanced traits. And traveling east into Asia, you'd find apes like Pithecus in India and Pakistan, whose facial structure is so strikingly similar to the modern orangutan that most scientists agree it stands near the very base of the orangutan family tree. For several million years, the ape experiment was no longer just African, it was Eurasian too. Evolutionary history is filled with strange side stories, and the Miocene apes give us one of the best. On what was then a swampy, isolated island in the Mediterranean, what we now call Tuscany, Italy, lived a truly bizarre ape called Australopithecus, nicknamed the Cookie Monster for its flat face and unusual teeth. It evolved in isolation for millions of years,
developing incredibly long arms for swinging through its swampy forest home. But its pelvis is the most intriguing part. Some scientists argue that its shape suggests Australopithecus may have evolved a form of awkward, shuffling bipedalism, completely independent of our own lineage, perhaps to help it wade through wetlands. It was a weird and wonderful experiment, but like so many others, it ended in an evolutionary dead end. This golden age of ape diversity, this vibrant, globe-spanning community, was not destined to last. Toward the end of the Miocene, around 10 million years ago, Earth's thermostat began to drop. The planet entered a long period of cooling and drying. Ice caps formed at the poles, locking up vast amounts of water and making the global climate more arid. For the apes of Eurasia, this was an apocalyptic event. Their world, the endless subtropical forests, began to wither away. The great green canopy broke apart into isolated patches, separated by growing grasslands and open woodlands. For creatures that had specialized for millions of years in eating soft forest fruits, this was a catastrophe. Their food sources vanished. One by one, the Eurasian apes disappeared from the fossil record. Dryopithecus, Pierolopithecus, Australopithecus, and many others could not adapt to this cooler, more seasonal world. They went extinct. The great Eurasian ape experiment had failed. Only 2 regions on Earth remained as refugees, places where forests endured. The tropical belt of Southeast Asia, where the ancestors of orangutans and gibbons survived, and equatorial Africa. Africa, thanks to its vast size and equatorial position, kept a variety of habitats, from dense jungles to open woodlands, that allowed its native apes to weather the storm. The climatic crisis had effectively pruned the great bushy tree of ape evolution, cutting away nearly all of the Eurasian branches. The stage, once global, was now dramatically simplified. The spotlight of primate evolution and the focus of our story shifted back to the continent where it had all begun, Africa.
The great Eurasian ape experiment was over. The climatic purge of the late Miocene had reset the board, leaving Africa once again as the primary stage for the final act of primate evolution. You are now entering this crucial moment, a period of transition between 8 and 7 million years ago. The world is quieter now. The once vast diversity of apes has been greatly reduced. Across the African continent, a successful population of large-bodied apes thrived, spread along the equatorial belt. But unseen forces, deep within their DNA and deep within the Earth's crust, were about to split this population in 2, sending each along radically different evolutionary paths. One path would lead to our closest living relatives, the chimpanzees. The other would lead to us. For a long time, the timing of this monumental split was hotly debated, based on sparse and often uncertain fossils. But in the late 20th century, a new kind of evidence emerged, not from rocks, but from our own cells. This was the evidence of the molecular clock. By comparing the DNA sequences of modern humans and chimpanzees, geneticists can count the number of differences, the tiny random mutations that have accumulated in each lineage since they diverged. Knowing the average rate at which these mutations occur, scientists can calculate backward to find the point of separation. The clock is constantly being refined, but it consistently points to a split somewhere between 7 and 8 million years ago. This marks the genetic birth date of our own lineage, the hominins. So what did this last common ancestor, the creature that gave rise to both chimpanzees and humans, actually look like? While we haven't yet found its definitive fossil, we can paint a fairly detailed picture based on genetics and the fossils of apes that lived around that time, like Australopithecus from Kenya. It was likely a strong, robust animal, about the size of a modern chimpanzee. It would have been an able climber, spending much of its time in the trees feeding on fruit. But it was also probably a knuckle walker, using the thick bones of its knuckles to support its weight while moving on the ground, just as gorillas and chimps do today. Its diet was likely generalized, made up mostly of fruit, but supplemented with tougher foods like leaves and stems when preferred foods were scarce. It was a successful, adaptable African ape, perfectly suited to its world. But that world was about to be torn apart. The agent of this change was the Great Rift Valley, the primary geological engine of human evolution. Imagine the entire eastern third of the African continent slowly being pulled away from the rest. Two massive tectonic plates, the Somalian and Nubian plates, are moving apart. As they separate, the crust between them stretches, thins, and fractures. The valley floor sinks thousands of feet, creating a vast, sunken landscape. Volcanoes, fueled by hot magma rising from the mantle below, erupt along the rift's edges, spewing ash and lava and building towering mountain ranges. This isn't ancient history. It's a process still happening today, slowly splitting Africa in two. This colossal geological upheaval had a profound and immediate effect on the climate. The rising mountains along the western edge of the rift created a rain shadow. Moisture-laden winds from the Congo rainforest and the Atlantic Ocean were forced upward by the new mountains. As the air rose, it cooled and released rain on the western slopes, nourishing the dense jungles there. But by the time that air descended into the Rift Valley to the east, it was dry. This rain shadow created two fundamentally different worlds. To the west of the rift, the old world of dense, continuous rainforest remained, home to the ancestors of chimpanzees and bonobos who continued their successful tree-dwelling lives. To the east, however, the environment was transformed. The endless jungle gave way to a patchwork landscape of scattered woodlands, river forests, open grasslands, and savanna. For the apes living on this eastern side, the rules of survival had changed completely. This new environment presented a terrifying, relentless challenge. The fruit-bearing trees were no longer part of a continuous canopy, but had become isolated islands of food and safety, separated by vast stretches of open, sun-drenched ground. To move from one tree to the next, they had to descend from the safety of the branches and cross open spaces where predators lurked and there was nowhere to hide. The old way of life, knuckle-walking and tree-dwelling, that had served their ancestors for millions of years, was suddenly no longer optimal. A new and radical solution was needed. The question hanging in the dry East African air was simple. How do you survive in a world that's falling apart? The challenge was set. In the fragmented world of East Africa, the old lifestyle was a dead end. The apes, stranded there by the geological upheaval of the Great Rift Valley, needed a new strategy, a radical solution for crossing those dangerous open spaces between trees. For decades, paleontologists searched for the first clues to this solution in the fossil-rich sediments of Kenya, Ethiopia, and Tanzania. Then, in 2001, the answer, or at least the first hint of it, came from an unexpected place. It wasn't found in the green hills of the Rift Valley, but thousands of kilometers to the west, in the scorching, sun-blasted sands of the Jurab Desert in Chad. The discovery, made by a team led by French paleontologist Michel Brunet, was a single magnificent skull. It was named Sahelanthropus chadensis, but is better known by its nickname Tumai, which in the local Goran language means hope of life. The name is profoundly fitting, for this fossil represents the very dawn of our own lineage, a symbol of hope. It was dated to between 6 and 7 million years old, placing it precisely within the time window when geneticists believe the human and chimpanzee lineages split. Its discovery in Central Africa was a shock, instantly challenging the tidy East Side story that proposed hominins evolved only in the Rift Valley. Instead, it suggested that the earliest chapter of our story was a much broader, Pan-African event. When you look at the Tumai skull, you see a creature of two worlds, a perfect mosaic of ape and human-like traits. In many ways, it looks like an ancient ape. Its brain case is small, about the size of a modern chimpanzee's. It also has a massive bony brow ridge, thicker and more prominent than any living ape's. If you saw just the back of the skull, you might think it belonged to an ancestral gorilla or chimp. But when you look at its face, the story changes. The face is surprisingly flat and short, lacking the projecting snout typical of other apes. Its canine teeth are smaller and less dagger-like, features that point, however tentatively, toward the human family tree. But the most important clue isn't on its face, it's underneath. The single most telling feature for identifying a bipedal creature from its skull alone is the position of the foramen magnum, Latin for great hole. It's the opening at the base of the skull where the spinal cord exits the brain and enters the spine. Think for a moment about how a chimpanzee holds its head. Its spine connects from behind at an angle, so its foramen magnum sits toward the back of the skull. Now think about humans. Our spine is positioned directly beneath our head, balanced on top of it. So our foramen magnum is located at the bottom center of the skull. The difference between a rear-facing and a downward-facing foramen magnum is the difference between a knuckle walker and an upright walker. And this is the secret that Tumai revealed. Its foramen magnum isn't at the back like an ape's, nor directly underneath like a modern human's. It's significantly shifted forward, an intermediate position. That placement is powerful evidence, the smoking gun. It strongly suggests that Tumai's spine was more vertical, that it held its head upright in a way no other ape did. It's compelling proof that this 7-million-year-old creature was beginning to abandon the ancestral posture of its knuckle-walking cousins. It's the first hint of the radical solution to life on the savannah: stand up. Of course, a discovery that rewrites the first page of human history is bound to be controversial. The debate over Tumai's locomotion continues. Some scientists argue that the skull was crushed and distorted during millions of years underground, that this distortion might make the foramen magnum appear more forward than it truly was. They point to its ape-like features and suggest it might belong to the gorilla line, or something else entirely. But its proponents maintain that even accounting for distortion, the evidence for a more upright posture is clear. Combined with its human-like face and teeth, they argue that Tumai remains our best candidate for the earliest member of our family, the first to take that tentative, world-changing step toward walking on 2 feet. While the debate over Tumai's skull continues, the fossil trail doesn't go cold. Moving forward 1 million years, to about 6 million years ago, new clues emerge from the heart of the Great Rift Valley, adding more weight to the idea of an ancient upright ape. In Kenya's Tugen Hills, fragmentary fossils discovered in 2000 earned the creature the nickname Millennium Man. Its scientific name is Orrorin tugenensis. And while we don't have its skull, we have something perhaps even more revealing: its femur. The femur, or thigh bone, is a marvel of biological engineering, and its internal structure records the forces it endured during life. The key part is the femoral neck, the angled section connecting the long shaft to the ball joint that fits into the hip socket. In a quadrupedal ape, stresses on this neck are evenly distributed, but in a biped, the entire body weight presses down on this joint, creating intense stress on the bottom and tension on the top. To counter this, the cortical bone, the dense outer layer, becomes thicker on the bottom than on the top. Using industrial CT scanners, scientists examined the fossilized femur of Orrorin. The results were stunning. The cortical bone distribution showed the same asymmetrical pattern seen in creatures that regularly bore their weight on 2 legs. The evidence was no longer just on the outside, it was deep inside the bone itself. The clues from Tumai and Ororin were tantalizing but fragmentary. The next discovery, however, would be a bombshell. It would provide the world with the first reasonably complete skeleton of an early hominin, a creature so strange and unexpected that it would force a complete rethinking of our origins. We now jump forward to 4.4 million years ago, in the Afar region of Ethiopia. Here, after years of painstaking excavation and reconstruction, a team of scientists unveiled a partial skeleton nicknamed Ardi. Her species is Ardipithecus ramidus, and she is one of the most important fossils ever found. Ardi was a creature of contradictions, a biological paradox that makes perfect sense only in the light of evolution. When you look at her pelvis, you see the undeniable beginnings of our own anatomy. The upper part of the pelvis, the ilium, is short and broad, reshaped to help stabilize the torso for upright walking. Her skull, like Tumai's, sat atop the spine in a way that suggests bipedalism. If you saw only her pelvis, you would confidently say she walked on two legs. But then you look at her feet, and the story gets wonderfully complicated. Ardi's feet were not built for efficient walking. They were built for climbing. She had a fully opposable big toe, a divergent hallux that stuck out from the side of her foot like a thumb. This grasping toe would have been useless for pushing off the ground during a stride, but it was the perfect tool for gripping branches. Her fingers were also long and curved, another classic adaptation for life in the trees. Ardi was not an ape slowly turning into a human. She was something else entirely, a creature exquisitely adapted for two different worlds. Her discoverers described her as a multi-use vehicle, built to move on the ground, but still excellent for off-roading in the trees. On the ground, she would have walked upright, though with a strange flat-footed gait, unable to push off her toes as we do. Then, upon reaching a clump of trees, she could effortlessly transition to climbing with all four limbs, using her grasping feet and hands to navigate the canopy. This shows that the transition to bipedalism wasn't a clean break from the trees. Our earliest ancestors didn't simply stand up one day and march out onto the savannah. They were hybrid creatures for millions of years, maintaining a foot in both worlds. Ardi's skeleton also presented a bold fringe idea that, if true, would upend a century of scientific orthodoxy. A central assumption in human evolution has always been that our ancestors passed through a knuckle-walking phase like modern chimps and gorillas. But Ardi's discoverers, after studying her wrists and hand bones, argued that she showed absolutely no adaptations for knuckle-walking. This led them to a radical proposal: perhaps our lineage never knuckle-walked at all. They suggest that the last common ancestor we share with chimps was not a knuckle-walker, but a more generalized four-limbed climber, and that knuckle-walking is a specialized trait that chimps and gorillas evolved independently after our lineages split. In this view, bipedalism evolved directly from a more ancient form of climbing, a fascinating idea that remains highly controversial, but serves as a powerful reminder of how much we still have to learn. The fossilized bones of Tumai, Ororin, and Ardi have given us the what, the where, and the when. We know that as early as 7 million years ago, in the woodlands of Africa, our ancestors began the slow, tentative process of standing up and walking on 2 feet. But this only deepens the central mystery. It forces us to ask the biggest and most difficult question of all: why? The quadrupedal, knuckle-walking posture of the great apes is a time-tested and highly successful mode of locomotion. Why abandon it? Why take up the awkward, unbalanced, and injury-prone act of bipedalism? There must have been a powerful and persistent evolutionary advantage to taking those first upright steps. The answer, it seems, lies not in one single cause, but in a combination of powerful environmental pressures. For over a century, the simple and intuitive answer was known as the savanna hypothesis. You've probably heard it. The forests shrank, thanks for watching. Wait for second part, thanks a lot.